Okay, what's up, everybody? Welcome back. And today I'll take some time to explain something I think I'll explain it real quick. But I think it's very important if you're like me and you're trying to develop a framework or software that is supposed to be identifying the specs of your machine, then determine what will be the best way of using your machine based on your specs. Like over here, I'm talking about uh, parallel computing, right? The idea here is like when you do some HPC work, and let's say you are an HPC engineer, and what you're trying to do is understanding the performance of an algorithm based on how it performs on different processes, or how it performs when maybe you look at you know different type of machine with the same number of processes, which means maybe you are thinking about what would be the impact of changing like the bandwidth, the latency, uh, communications. What would be the difference if you change, for example, the per byte transfer time when you have zero copies or when you have copies, or the startup message latency. What is the difference when you change those parameters? Which means what is the difference when I change the machine? So for different type of machine, different type of CPUs, you can set up the same number of processes and see how it perform on different machine. Or for the same CPU or same machine, you can change the number of processes and see how your algorithm performs, right? The idea behind doing those experiments is usually most of the time people are doing it for benchmarking, but you can also think about doing it just for understanding how your algorithm is capable of, co- copying, or maybe copying in this not it's not appropriate in this case, because we want to think about the ability for the algorithm to adapt to different type of machine. So how do I use polymorph in this case? You know, you want to have that ability. So if I change the machine, I still want to be able to use the algorithm in an optimal way. And so that is another reason why you want to do those experiments. So now, what is the end of it? For some people, again, like I said, benchmarking is the end. For some other people, it's the scientific uh, substance behind those experiments that is the end. Trying to push the science of developing this HPC architecture, like forward. For some other, like I think for me, another goal could be for people who are developing software. I take a short example. If you do mining projects and you have to use your laptop for estimating, I don't know, grades, right? Or tonnage. I think if you have a very large domain that you are exploring, and you want to be able to simulate, for example, and you don't want to waste time when you're running your simulations, this is one way of doing it, right? You can think about how you would do it like in using parallel computing, like in this manner. But now the problem is, do I need, do I always need to spend a lot of money trying to get the highest laptop in the market in terms of memories, CPUs? Or do you think it's possible to get a decent laptop? Let's say I am not a big company. I'm like maybe a startup. Do you think it's possible to get a decent laptop, maybe with, let's say, 20 CPUs and still be able to do the job? And if it's possible, then where can I find experiments or a few examples trying to, show me how this is possible? And what kind of software am I going to use in this case? Because people usually, when they develop software, they don't really, I don't think they will put in mind the fact that maybe you want a software to be able to identify the specs of your laptop before it can actually do anything. And what would you do with those numbers? Those numbers are supposed to be a way to tell you, well, maybe if I want to do something in parallel, I cannot use 14 processes because in this one I only have 12 CPUs. Most likely four of them are used just to run the your OS, and the remaining one you can use now for any other job. So maybe for like something with 12 CPUs, I just want to use six processes, right? And why not 14? Well, if you use 14, first of all, you will use 12 instead of 6. So even those that are used by the OS are going to be used by your program, but you will have two other processes waiting for one to complete before it can actually start working. So you probably end up with synchronization problems, I think, especially for laptops, because I don't think laptops are working the same way servers are working. Like if you have a cluster, it's different than what you have in a laptop. I don't want to go into details about the difference when, if I think, for example, you have a, like there was this infrastructure called CCR. The way CCR works is not the same as the way your laptop is working in terms of parallel computing or, using different CPUs or different processes. It's very different. I'm not going to I'm not going to go into details about those. So what I will show you today is just very, very, very simple. And next time, maybe I will show you how you can, use what I will show you today. And the idea is just, I don't, okay. This is for Linux, specifically Ubuntu. I don't think I know how to do it on Windows. And my guess is that if I can do it on Ubuntu, I might be able to do it on a Mac, because right now I think the Mac, the OS has like Linux behind, so you might be able to run some bash command when you run your Mac. So you have to open the terminal and you should be able to run. Although I'm not sure you will have this specific command in your Mac, so I will have to double check if I was you. But basically, that's what I will show you today. So you see this command lscpu. It's supposed to give you the characteristic of your machine. So it will give you the architecture, the CPU OP modes, the address size, the bit order. What is very important after these two lines, to me, they are the two CPUs and online CPUs, just to see the numbering. Very important. After that, you have three lines. Okay, over here is four, giving the memories of the cache. So you have the L1, L2, and L3. If you don't know what these are, I can maybe take another video to explain. But so now, let's say I have a software that is running Kriging in parallel, and I want it to be able to use. I want my software to use a number of processes consistent with how many CPUs I have. So if I have 12, I don't want to use more than 80% of this number, right? So the way you do it, you can use a command like this, lscpu, and put all these in spec.txt, a text file, which is what you have here, and you can read a text file line by line, right? So I can read this and just grab these two lines and grab, where do I have the L? Yeah, and grab these two lines, and probably also these two. I mean, these three lines are, and well, four lines. I'm tired. And probably also these two lines, right? And put these numbers into different variables. Now I can use them, because you remember when you run let's say I'm implementing my parallel programming with MPI. When you run MPI, you can call in different parameters in your script, in your main script. So these numbers can be those different parameters. And so you don't have to manually set a value for your MPI program, especially because you're doing it in our local machine, like it's local. So you can just grab these numbers, take 80% or less for your algorithm and do the job. So now, what is the advantage of doing this? Obviously, the advantage is going to be you can always have a good performance in a decent laptop. This laptop is not adapted for, this is a Dell Inspiron 14. It's really not adapted for HPC stuff, right? Still, if I want to, I know how many CPUs I have, and I know how much I can, you know, uh, move around in my machine when I use these CPUs to do parallel programming. And so now the idea is, you're not going to match the power of, uh, like a big infrastructure with several nodes, right? Still, you can use this decent laptop to get the job done in an efficient way. And so, like I said, this could be an option for those who are like short in terms of funding to get like a very powerful laptop, or those who are short in terms of funding to have access to those big hubs and those big nodes. And so you can find a way to use your laptop to do these jobs. Maybe you will have to wait longer than some other folks, but the idea is that you still can do it with your decent laptop. Now, I'm not saying you will have something with three cores or three CPUs and you will try to do this. It doesn't make any sense, right? Try to have something at least like this, like at least 12 CPUs, and think about using 8 of them for your job. Or 4, it depends. I think I was getting some pretty decent numbers with 4 CPUs when I was doing variant modeling, and I was using 300,000 points, which is already huge, even for mining project. This is those 300,000 points. They were coming from those satellite altimetry data points. So mining projects, I don't think they will get to that level of uh, dimensionality. So yes, you can do it with a decent laptop. That's what I wanted to say. And this is how you can do it. I think there are other commands that you can use to grab these numbers, but I feel like this one is very simple to use. It's just one line, and that's it. And you can do everything else. So maybe what we can do next, because I feel like I need to show you how you can actually use this file, right? So maybe what we can do next, I have a program for Paradigm modeling. So I can grab that program and take this file and just, automatically push a number of CPUs as, not the number of processes that the program can use. So we can do that. I think it's gonna be fun. So next time, that's what we will try. And next time I can also take some time to explain a little bit more about, communications and all those stuff. Right. So see you next time.